Welcome to ECE 302. This is lecture 2.6 on Bayes' theorem and total probability. I am Professor Stanley Chan. This is lecture 2.6. If you recall our previous lectures, this is the third part of our discussion on conditional probability. In section 2.4, we talk about the meaning of conditional probability, and this is a very easy definition that you take the intersection of two events and then you divide it by the other event. In section 2.5, we introduced the concept of independence. That's also relatively not too hard in the sense that if two events are independent, you can factorize the probability into a product of the two individual probabilities. In this section, we are going to learn a very useful technique that can help us link conditional probability, independence, to practical problems. Now, to motivate our discussion, I want to talk about one very specific problem. The problem is called the prisoner's dilemma. The goal of this problem is to show you the difficulty of using conditional probability and independence to make reasonings. And you will see that to solve this problem, we need some new tools. And therefore, I'm going to introduce the Bayes' theorem and also the law of total probability. And then afterwards, we are going to look at a few examples. And then finally, we will come back to the prisoner's dilemma and explain how we can solve the problem. So to start with, let me describe the problem. So imagine that there are three prisoners, A, B, and C. Okay, so let us draw the three prisoners. So prisoner 1, prisoner 2, and prisoner number 3. Okay, so they are A, B, and C. And then the king decides to release two of those, and then he's gonna sentence one. All right, and so among the three, two will become happy, and then one will be unhappy. Okay, and so among all these ABCs, let's say you are A, and then your chance of being released is 2/3. Okay, I think this is very clear because there are three people. Two will be released, one will be sentenced, and then if you are one of those, then your chance of being released is 2/3. Now, suppose you know a guard, okay? And so here is a very happy guard. All right. And so you can ask this guard whether A or B or C would be released. Well, in fact, you can only ask him about whether B or C will be released because you are A. Okay, so you approach to the guard. You don't know whether you will be released or you will be sentenced. When you go to the guard, you will ask, can you tell me something about my two buddies, B and C? Okay, so if you walk to him and you ask, can you tell me whether B or C will be released? He is going to tell you either B or C. Okay, so let's see if the situation is that you are a happy face and then C is the unhappy face. then he's going to tell you B will be released. Okay, or if you are the unlucky person and then B or C are the happy person, he's going to tell you maybe C will be released. Okay, so no matter what the situations will be, he will tell you one. Okay, so among the three, you can eliminate one of those, right? Because you talk to the guard, and then the guard will help you eliminate one person for sure. And so now your chance being released will drop from 2/3 down to a half. Okay, because you knew that C will be released, then it is a game between you and B. So your chance of being released is reduced. Okay, so how come this will happen? Okay, so we want to ask this question. Why is that going to the guard will change the probability of being released? Is actually reducing the probability from 2/3 to a half. So at this moment, I believe many of you who are watching this video will start to think something should be wrong in this problem, and precisely what is wrong in this problem remains unclear. And my hint to everyone is that we need to use whatever we have learned, in particular, the conditional probability and also independence, to help us analyze this problem. So if you think that independence and conditional probabilities, they are very easy topics, then can you help me solve this problem? So I'm not going to solve this problem right now. What I want to do is to briefly talk about some of the steps. And then we are going to learn some new mathematical tools. And then we'll go through some examples. Then we will come back to this problem and discuss how this can be solved. So let me just introduce a few notations to set up the playground, and then I'm going to discuss some mathematical tools. I am going to define three events: event XA, event XB, and event XC. These events represent the situation where the king will sentence prisoner A, B, or C. There is another event called a GB, where the guard says B is released. So we want to analyze all these probabilities, but at least there are something we can talk about. What are they? Well, these probabilities we can easily calculate. So the probability of XA is the probability that the prisoner A will be sentenced. This is happening without talking to the guard. Okay, so no matter what the guard is going to tell you, this is the decision that comes from the king. And so what is this probability? This probability is not influenced by the guard at all, and we know that this is 1/3. Okay, and this number is also true for XB and XC. All right. Okay, so this should be very clear. Probability of XA, XB, and XC, they are all 1/3. So this is one part of the story that we know without the presence of guard or absence of guard. XA, XB, XC, they all have probability 1/3. Now, let us also consider the following three conditional probabilities. These probabilities are the conditional probability that the guard says B is released when A is actually sentenced. Okay? Or the guard will say B is released given that B is actually sentenced. And C is that this third event is that C will be sentenced, and then the guard will say that B is released. So if you look at these three conditional probabilities, what do they really mean? It's a conditional probability. So there are two players. One is a very happy king who can decide whatever he wants to do. And then the other one is a very faithful guard who is going to tell you the truth. Okay? And so XB is really coming from the king, same for XA and XC. So the king can decide XA, XB, and XC. GB is what the guard can decide. Now, let us do some very simple calculation. For this event, let's look at this. Probability that prisoner B is sentenced, and then the guard will say that B is released. Okay, so imagine that you walked to the guard. The guard knows that B will be sentenced, and you ask, can you tell me whether B or C will be released? Now, because B will be released, will be sentenced, the guard knows that. The guard cannot tell you that B will be released. Okay, and so what is that probability? This would just not happen. Okay, so you can see that prisoner A, B, and C. You are A. You cannot ask anything about yourself. And then the king has decided to knock this person out. And so what can the guard say? The guard has to report you C. And so now you are asking whether the guard will tell you B, and the guard will never tell you anything about the B. Okay, so the probability of guard telling you B is released, given that B is sentenced, that is 0. We can also calculate the other probability, which is that suppose C is sentenced, and then what is the chance that the guard will tell you about B? In this case, the king has decided to knock out C. Okay, so C is knocked out. And then you are A, you went to the guard, you ask whether B or C will be released. And will the guard say that B will be released? Certainly, he has no choice, but he has to tell you that the person has to be released. Okay, so now we have already calculated these two probabilities. And then let us calculate one more probability. This probability is that you are actually the unlucky person. Okay, so now the king has decided to knock you out. And then you went to the guard. The guard will say either B or C. So what is that conditional probability? This is 1/2, because the guard can either tell you B or C. So at this moment, we have calculated two sets of probabilities. One is the conditional probability, which we have three numbers, 0, 1, or 1/2. The other one is the previous slide, where we have all these 1/3, 1/3, and 1/3 probabilities. Okay, so these are just setting up the playground. We still haven't been able to answer the question, what has become wrong in this dilemma? The ultimate thing that you really care about is the following conditional probability. It is the conditional probability that suppose the guard said that B will be released. And in fact, you are the unlucky person. All right, so let me write down this probability. It is the conditional probability of XA given GB. That is different from what we have just calculated. Okay, this one we know it is 1/2. But this is actually the probability that you care about. Why? Because there are 3 prisoners, and then there is a guard. And so when these people, when you went to the guard, and then the guard is going to tell you whether B will be released or not. Okay? And so when this has happened, we want to know whether this event will happen. And so you want to calculate whether this probability, this is the conditional probability, will actually give you 1/2. Because according to our hand-waving argument, since you have not now B, okay, because if the guard says that B is going to be released, B is no longer inside your consideration. Then you're competing with C, and so you tend to think that then your chance will come 1/2. Okay, so we ask, is this 1/2? Now, this question can only be answered if you're able to evaluate this probability. Okay, this conditional probability of XA given GB. But if you look at our discussion so far, we only have GB given XA, we have XA, we have other conditional probabilities, but we really do not have this conditional probability of XA given GB. And therefore, I will invite you to follow me to the next slide to talk about 2 mathematical tools to learn a technique. How do we translate from this conditional probability to the other conditional probability and back and forth? So let us go to section 2.6.2, which is the discussion on Bayes' theorem and the law of total probability. First of all, let me introduce this theorem. It's called the Bayes' theorem. The Bayes' theorem is a very powerful tool which allows you to switch the order of the conditional events. So the theorem states as follows. Consider 2 events, A and B, and also assume that they are non-empty. Then it holds that this conditional probability of A given B can be written as B given A times A divided by B. So the significance of this Bayes' theorem is that on the left-hand side, you have A given B. On the right-hand side, you have B given A. Assuming that you have access to PA and PB, then switching the order becomes very easy. So I'm going to prove this theorem, and you may wonder that this theorem may be very, very difficult to prove. But in fact, this theorem is actually quite easy to prove, and let me show you why. So let us calculate the left-hand side. This is the conditional probability of A given B, and let us multiply the denominator of the right-hand side, P of B. So here you have this product of conditional probability and this probability, and we know that by the definition of conditional probability, this is really just the intersection of A and B. Now, if you look at this intersection, certainly you can write in this way, A given B, but I can also write it as B given A times the probability of A. Okay, it's just another way of writing this intersection. And we have got to the result because you just move this to the denominator, then you will have this result. Okay, so this Bayes' theorem is literally just applying the definition of conditional probability, and then we're moving terms around. Then you will be able to switch the order of B given A and A given B. This is very useful. Now I'm going to introduce you to another very useful result. It's called the law of total probability. So the law of total probability, the notation might be a little bit complicated, but the concept is actually very, very simple. So assume that we have events A1 through AN, and they form a partition of the sample space. Let me remind you what is partition. Suppose you have a sample space. A partition is a collection of subsets A1, A2, A3, A4, and so on, where all these AIs, they are disjoint, meaning that they do not overlap. And when you take the union of everyone, it will give you back the sample space. So this is one example of a partition of a sample space omega. The theorem says that suppose you consider an event B, this is your B, your event B can be computed by this finite sum. In this finite sum, you are summing I from 1 to n, which covers all the n partitions. And then inside the summation, you have this conditional probability of k given ai times p of ai. So what are they? Well, if you recall the definition of a conditional probability, this is nothing but p intersect with ai. So going back to the diagram, here is B intersect with A1. Here is B intersect with A2. This is A3, and this is A4. And so your probability of getting a B, which is this circle, can be decomposed into many smaller events where each event is B given AI. And they can further be calculated using this conditional probability. Now, how do we prove that? The proof should be pretty straightforward according to this diagram, because if you start with the right-hand side, then each of these is the intersection. And so now you are summing over all these intersections. Notice that these intersections, they are disjoint because by construction, all the AIs are disjoint, and therefore B intersecting with AI is still disjoint. And so now you're summing many probabilities of disjoint events, and according to axiom number 3, this is the union of all the B intersecting with AI. This is axiom 3. And then what is the union of the sets? Well, that's just the set operation. When you have all these 4 subsets, when you put the union together, that will just give you B. And therefore, we have proved this theorem, this law of total probability theorem. Okay, so here is a diagram that also illustrates this law of total probability. We are really cutting the sets into 4 sections, and in general, you can have n sections. And each section is the intersection of B and the AI, and you're cutting them out. In each intersection, according to the conditional probability, you can write them as the conditional probability times the probability of having that segment. And therefore, when you add all these up, you will be able to get the probability of having this green circle. So now I have introduced these 2 mathematical tools. And you may start to wonder how we can apply these mathematical tools to solve the prisoner's dilemma. Bear with us for a few more minutes. Let me illustrate some examples of these 2 mathematical tools, and then we'll come back to the prisoner's dilemma. So here is the outline. We're going to look at two examples, and these examples will bring out the powerfulness of the two mathematical tools I just introduced. And then we will talk the prisoner's dilemma at the end. So the first example is a very easy example. Suppose that there is a tennis tournament. Your probability of winning the game is 0.3 against half of the player. We call this event A. 0.4 against quarter of the players, and 0.5 against the other quarter of the players. Okay, so these are event A, B, and C. So what do they mean? Well, you are a player, okay, and then of course there will be somebody who are better than you, somebody who are as good as you, and then somebody who are worse than you. So if you play against player A, which are the very, very good players, your chance of winning is 0.3. And then you know half of those, they are, let me just call them 50% of those players that are better than you. Okay, so if you play against them, you have 0.3 chance of winning. If you play against this type of players, there are 25% of players that belongs to this category. Your chance of winning is 0.4. And then there are another 25% players in category C. And if you play against these people, you have 0.5 chance of winning. Okay, so now we ask, what is the probability of winning the game? Okay, so because when you enter the game, you don't know which person that you are going to compete. So there is certain chance that you will compete with A, certain chance competing with B, certain chance competing with C. And if you were selected to compete with A, your chance would be 0.3. Okay, so how do we calculate the probability of winning the game? Now, to do this problem, let us define three events. Okay, A is played with A. Okay, B is play with B, and C is play with C. Okay, so the probability of A is 0.5, or let's just write it 1/2. Probability play against B is 1/4. Probability of play against C is 1/4. Okay. Now, how do we quantify these three numbers, 0.3, 0.4, and 0.5? These are the conditional probabilities. So suppose we define W as win. Okay, so we can calculate what is the probability of winning given that we're playing against player A. And according to the problem, this is 0.3. And then we can also calculate the probability of winning given B. This is 0.4. And then the probability of winning given C, this is 0.5. Now, we want to calculate what? We want to calculate the probability of winning. This is an unconditional probability. So how do we go from these individual probabilities and also all these conditional probabilities to tell us the unconditioned probability? So according to the Bayes theorem and also the law of total probability, we know that this unconditioned probability can be written as the probability of W given A times the probability of A plus the probability of playing against B times P of B plus the probability of W given C times the probability of C. Okay, so this is just the law of total probability. So now let us put in the numbers. here we will get 0.3 times 1/2 plus 0.4 times 1/4 plus 0.5 times 1/4. And then if we carry out the calculation, this is 0.15, this is 0.1, and then this is 0.125. And so if you add the numbers up, this will give you 0.375. Now, we can also ask the other probability. Another probability that we can ask is the probability of A given W. What is the meaning of this probability? This is the conditional probability that suppose that you have won the game, and then someone asks you, what is the chance that you actually played with A? So now you can see that this probability is just the flipped version of the probability here. And what we can do is that we can apply the Bayes theorem to help us compute this probability. So what is that? We can use the Bayes theorem to show that this is equal to W given A times the probability of A divided by the probability of W. So what is W given A? This is 0.3. PA, this is 1/2. And then PW, we have already calculated the number, which is 0.375. And so you can complete the calculation by yourself. So now let us consider another example. In this example, we are studying a communication channel. The probability of sending a 1 is P, and then the probability of sending a 0 is 1 minus P. So this is a digital communication channel where you are sending 1 and 0. You are either sending 1 or 0. The chance of starting with 0 or starting with 1 is P and 1 minus P. You have certain probability to make mistake. For example, if you start with 0 and then you transmit through the channel, you go to the other side, and then your bit got flipped because of the error, the chance of happening is epsilon. If you start with 1 and then you go to 0, the chance of happening is eta. If you got correct transmission, is 1 minus eta and 1 minus epsilon correspondingly. So we ask several probabilities. What is the probability that you will receive a 1? What is the probability that you have actually sent 1? What is the probability that you send a 1, but now you receive a 1? And what is the probability that you received 1 and then you are you actually sent 1? Okay, so these are different versions of the conditional probability. And if we can understand how to calculate these probabilities, we will be much better equipped to answer the prisoner's dilemma. So let us try to answer these problems one by one. Let us start with this probability. The probability that you are sending a 1. Now this should be very straightforward because the sender has nothing to do with the channel, and so this is just P. Okay. All right. So now let us also consider this event. Suppose that you have already sent a 1. So you're now here, and then the receiver is receiving a 1. Okay. So given that S is 1 and that R is also 1, what is that probability? This is just 1 minus eta. It has nothing to do with this 1. Okay, the 1 is already there because you are conditioned on the event that you're sending a 1. So this conditional probability is just 1 minus eta. And then what is the probability of receiving 1? Now, to answer this question, we know that the probability of receiving a 1 can be written as the probability of receiving a 1 given that you actually send a 1 times the probability of sending a 1 plus the probability you receive a 1 given that you send a 0. Okay, so what is this equation? This is the law of total probability. And do we have all these numbers? Yes, we have all these numbers. Now, what are these numbers? The first number, this is that you send a 1 and you receive a 1. We just calculated that this is 1 minus 8. The probability of sending a 1, this is P. The conditional probability of R equals to 1 and S equals to 0, we can actually go back to the diagram here. S is 0 and the R is 1, okay? And that length is epsilon. So you have epsilon, and then S equals to 0. This is just 1 minus P. So you have 1 minus P here. So this is the probability of R being 1. Now, how about the last one? The probability of sending a 1 given that the receiver is receiving 1. So you want to find S equals to 1 given that R equals to 1. And by the Bayes theorem, we know that this can be written as R equals to 1 given that S equals to 1. We're switching the order times the P of S equals to 1 divided by the probability of R equals to 1. And do we have all these numbers? Exactly, we do have these numbers. Why? Because this quantity is just 1 minus eta. S equals to 1, this is P. And then the probability of R equals to 1, we just calculated, is 1 minus eta times P plus epsilon times 1 minus P. Okay, so we have calculated all these probabilities. So this example also demonstrates the usage of the law of total probability as well as the Bayes theorem. Now, let us come back to the prisoner's dilemma. In the prisoner's dilemma, we talk about this conditional probability. We want to calculate the probability that prisoner A is executed given that the guard says B. So how do we calculate this conditional probability? With the tool of the Bayes theorem, we know that this is G of B given X of A times the probability of X of A divided by the probability of GB. So we know that this number is that the actual person got sentenced is A, and then the guard will say B, and we know that what is that probability? This is 1/2. And here is just the unconditioned probability that the probability that A will be sentenced. So this is 1/3. So these will come from the top slice. Now, what about this probability? This is unconditioned probability of GB, but we do know how to calculate GB because the probability of GB is the probability of GB given XA times the probability of XA plus the probability of GB given that XB times the probability of XB plus the probability of GB given XC times the probability of XC. This is the law of total probability. And so now let's plug in the number. This is 1/2. This is 1/3. This number is what? The person is sentenced, B is sentenced, and then the guard will never tell it is B. And then this is 1/3. And then here it will be 1, and this is 1/3. Okay, so we can calculate all these numbers. This will give you 1/6 plus 0 plus 1/3. And what will that be? It will become 6. This is 1 plus 2, so you get 1/2. Okay, so let's go to here. This is 1/2 times 1/3 divided by 1/2. Okay, and so now we can cancel out these two terms, and we see that this is the guy. Okay, so the conditioned probability of XA given GB is 1/3. Now recall our hand-waving argument. What was the number that we originally argued? We were saying that this number is 1/2, because if you knock out B, if the guard tells you something about B, you're only competing with C, and so your probability is 1/2. But with all this careful calculation, the answer shows that it is actually 1/3. What is so special about this 1/3? This 1/3 is the probability of XA given GB. But this probability is also the probability of XA. Okay? And what is the meaning of these two? This equality says that the presence or absence of the guard does not influence the probability that A will be sentenced. And therefore, XA and GB, they are just independent events. Okay? And since they're independent events, these two numbers should be identical. And so there isn't any dilemma, no matter you have talked to the guard or not, because the guard will never change the mind of the king. The probability, regardless whether you are conditioned on the guard or not, this is always 1/3. So this lecture concludes that how do we use the Bayes theorem and also the law of total probability in conjunction with the conditional probability and independence to solve problems that may not be so obvious at the first glance. So I hope you have enjoyed this lecture, and if you have any question, we welcome you to post questions on our class Piazza, which is exclusive to our Purdue students, or you're welcome to send us emails. And we'll be very happy to help you out on this lecture. And I will also encourage everyone to try our homework set and make sure that you really understand the concept. Thank you.